Hello everyone, this is the video lecture of section 8.6, part 1 of Calculus 2 Math 2520. Okay, here. So in section 8.5, we introduced power series as some special kind of a function, okay, given by a series involving x, okay? And also we learned how to get the domain of power series, usually using ratio test. Okay, so in section 8.5, you were given a power series, kind of like a polynomial of infinity, right? So it is because infinite series. This is a function whose value is the sum of the series, okay, for given x value for which the series convergent. So the powers is given, and then we want to analyze how to make sense out of it, right? For what kind of value of x it is convergent, all right? So that's why we talk about radius of convergence and interval of convergence. Now, this section we change perspective. Now we have a function normally given, explicit form of a function. And then we ask ourselves, is it possible to write the given function as power series, okay, whose sum of power series is the same as the given function, okay? So that's the question, main question in this section. And then the starting point will be geometric series, a rational function. If you have x to the n, 1x, x squared, that's infinite series. This is geometric series with radius of common ratio x. Therefore, this must be first term over 1 minus common ratio, right? But this convergence works only when absolute value of common ratio less than 1. That means between -1 and 1. So, for any value of x between -1 and 1, this power series, same as this rational function, okay? So we have this. And this is the basis of everything comes after this, okay? Power series of rational function 1 over 1 minus x equals sigma x to the n and runs from 0 to infinity, okay? For this, as long as the number, okay? Now, then we want to extend this techniques to slightly more broader, right, class of rational functions. For example, this example 1, can we find the power series representation of this rational function? So now you have to read this one carefully. This means that 1 over 1 minus something is equal to something to the nth power runs from 0 to infinity. As long as absolute value of something is less than 1. So we want to write this one as 1 over 1 minus negative x squared. This is that something. So according to this, it means that's something to the nth power. As long as that something is absolute value something is less than 1, right? Now, if you want, you can rewrite it. Minus 1 to the nth, x to the 2th, right? So that would be power series representation of this one. If you want, you can write it a few terms. basically you replace x with negative x squared. So 1 minus x squared plus x to the fourth and so forth. This one, we don't need absolute value. You know, how do you solve this inequality? 0, right? So x plus 1, x minus 1. So, still 1 and negative. Or you can say that, I mean, absolute square root of x squared is x squared. Absolute value of x. Square root of 1 is 1. So, or you can still write it. So, interval convergence is same as the first one. Because 1 squared equals 1. And instead of x, you have a minus x squared. So anyway, so we just used this simple formula, infinite geometry series. All right, this is just a little bit of adjustment. Our next example requires slightly more adjustments, like this. Okay. All right. Again, this is our starting point. 1 over 1 minus something. That's the form we want to rewrite. Unfortunately, this is not 1. Then we can write factor of 3. We can write it this way, right? So we just take up 1/3, then 1 over 1 minus something, right? Now we can use this. So this must be 1/3 out and runs from 0 to infinity. All right, that's something. X over 3 to the nth power. Or you can write it as x to the nth, 3 to the nth. Probably the most appropriate form will be take this one in 1 over 3 to the n plus 1 times x to the n. This is so-called Cn, coefficient. It's x to the nth. All right. Now, then the interval of convergence is determined by this. The absolute value of something. Something is x minus 3. Yes, something. Absolute value is less than 1. Right? So multiply both sides by 3. So for x between -3 and 3. Okay? Alright. The interval of convergence is -3 and 3. Radius of convergence is obviously 3 as a power series. Now, in this case, it's not the only way you can find the power series representation. What if we do this? Okay, 1 minus something. I can write this one as 1 plus 2 minus x. And then I write it, this one is 1 minus of x minus from these two. Take out negative 1. Okay? Then now we have, again, 1 over 1 minus something. So it must be something to the nth power. Now this is a power series centered at 2. This is power series centered at 0. Right? So the expansion point is different. Here is 0. Here you have 2. Also, we have to satisfy absolute value of something is less than 1, right? When you write 1 over 1 minus something, 1 over 1 minus this, absolute value of this is less than 1. So the radius of convergence is 1. And this means that x minus 2 is between 1 and -1, 3, and 1. This is interval of convergence. Okay? So, for the same function, you could have different power series when you choose different expansion points, different center of expansion. Okay? And then your, obviously, interval convergence will be different, and even radius of convergence is different. Now, one interesting remark is that when you draw y equals 3 minus x, this is -1 over x minus 3. So, you know, asymptote is x equals 3 minus 1, so you will have something like this. Okay? Graph will be like this. So, it is interesting that in this expansion, you're capturing 3 to -3. This part, your function keeps going, but our power series captures this part. It has to stop at 3. You cannot cross 3 because your function is not even continuous. Okay? So it is stopping here. So when you expand around 0, you can go all the way to up to 3 before you hit the wall, right? Vertical asymptote. Now if you start from around 1, around 2 actually, this is 2, this is 3. Then from 2 you can go only up to 1, distance 1, before you hit the wall. That's why you have to go both sides, the same distance. -1 and 1 and 3. Okay? So when your expansion point is close to 3, then your expansion point can be only as your size. Radius convergence can be only up to 1. Right? So it's not a coincidence. This is the general feature, actually. That's the notes I put in the middle of the second page. Okay? Now, example 3. Example 3. A. You have x squared over 1 minus x. B. 1 plus x over 1 minus x. Let's do A first. So these are all based on this simple formula of geometric series, sum of geometric series. Now let's take a look at this. First of all, you can write it as x squared times 1 over 1 minus. And 1 over 1 minus, we know that x to the nth. Okay? So we can write it. This constant can be taken in, this one can be taken in, so x to the n plus 2. Alright? Now, of course, absolute value of x less than 1. Now, that is actually x squared plus x to the third plus x to the fourth. Or we can write it, this one is n runs start from 2 to infinity, x to the n. Either way is fine. Okay? And so interval of convergence is again -1 to 1. Okay? It's just a x squared multiplied to 1 over 1 minus x. So nothing surprising. What about this one? B. Let's do it over here. Before that, let me check the video recording. B was, example 3, B was 1 plus x over 1 minus x. Now, let's do this. 1 minus x plus 2x. I want to write it this way. Why? That I can split this way. So, what is it? 1 plus 2x times 1 over 1 minus x, isn't it? And we know this. This is, and from 0 to infinity, x to the n. So you can write it 2 times x to the n plus 1. Okay? And you can write this one as 1 plus 2x squared, 2x to the third. Keep going. Again, because of this, x can be only between negative 1 and 1, right? So you get this. This is your power series representation of this, okay? For this radius of convergence 1. Okay? Now, there is an interesting also remark. Let's write this one as 1 plus x times 1 over 1 minus x. Okay? Then 1 plus x, what is it? 1x, x squared, x cubed, keep going. Power series representation 1 plus x. Now, let's assume that we can do distribution even between polynomial and power series, so that foiling is possible. Let's assume that. Then what do you get? 1 times this, 1 times x, infinite foiling, right? 1x, x squared, x to the third, keep going. From here, x times 1 is x, and then x squared, and then x to the third, keep going, right? If you add them up, what do you get? 1, and then 2x squared. Hey, this is exactly the same as the result we already have, right? And this is not coincidence. As long as this one is meaningful only here, as long as you have a conversion within the interval of conversion, infinite foiling is possible. Okay, we don't prove this stuff, but in more advanced math courses, actually you show that not only polynomial versus power series, but power series versus power series, still infinite foiling is possible within the interval of convergence. Okay? All right. Now, next one is, now let's say we have, think about it. If you have a polynomial, let's say, how do you get the derivative? We do this one instantaneously, even without thinking these days, but this is actually what happens. You take the derivative, split over addition, and then take care of differentiation separately. So it is 0, 1, 2x, 3x squared, 4x to the third. This is what we call linear property of differentiation. When you have a linear combination of functions, this derivative can be done as a linear combination of each derivative of each component function. Okay, so you know, basically you can split your differentiation over addition, constant can be taken out of it. All right, then our question is, what if you have power series. And if the power series is a function, right? Can we take the derivative? Just like this, term by term, so-called term by term differentiation, even though you have infinite many terms. That's the question. Would it be same? Now this one keeps going. Would it be equal? All right. The answer is yes, you can do that as long as you stay in the same radius. Actually, this one works. This is also power series representation of what was the original function? This was original function, right? It turns out to be that what's this? 1 minus x, -1, -2 times -1, right? So you have -1 over 1 minus x squared, right? -1, well, wait a second, no. -1 times this and derivative inside, so this one. So this is the derivative 1 over 1 minus x. And this is the derivative of term by term differentiation of the power series of the original function. It is known to be equal with the same radius convergence law. Okay? So, what we are trying to do is that if you have a function which has a power series representation, then that function has derivative, and its derivative has its own power series representation. And that power series representation of the derivative of the original function can be obtained by taking term by term differentiation of the power series of the original function. Okay? That's the content of theorem page, 4th page. Okay? Before we write those statements, same thing for this. If you have polynomial, you would do split over addition, right? This is the things you did automatically without even thinking these days. So you get some arbitrary constant times x, 1/2 of x squared, 1/3 of x to the third, 1/4 of x to the fourth. And the question is, what about infinite geometric series, which is, right? Would it be obtained term by term integration? Okay, 1 dx forever, c plus x plus 1/2 of x squared, 1/3 of x to the third forever, and the answer is yes. That would be ln of 1 minus x, right? 1 minus x, some constant. Well, because we only consider -1 to 1, we don't need absolute value because this will be anyway positive. And this thing will be power series representation of ln of 1 minus. So, just like differentiation, if you have a function f, it's power series representation. Now, you have an antiderivative, indefinite integral, an antiderivative of this function. This one will have also its own power series representation, and that power series representation can be obtained by doing term by term integration of the power series of the original function f. Okay? So, and then in that process, the power series representation of an antiderivative of original function f will have the same radius of convergence as the original function's power series representation. So we can summarize the result here as a theorem the main theorem of this section. Okay, that is theorem. Suppose that f of x has a power series representation. Cn x minus a to the nth power, which means c0, c1 x minus a, c2 x minus a squared, and so forth. Has the radius of convergence r. Now, we don't consider power series converges only at the exponential point a, like n factorial x to the n. It's only defined at one point. We cannot even talk about derivative or anything. That's uninteresting. So your radius of convergence must be at least some positive number, or it could be infinity, right? Or to make it clear, some positive finite number, real number, or infinity. Then graph of x is differentiable on this open interval, a minus r, a plus r. We don't consider derivative at the endpoints, right? So only interior from a plus minus r. The interior of interval convergence. Interval convergence can have one or both of the endpoints, or maybe not. But anyway, differentiation is only done interior points, right? So any function which has power series representation is automatically differentiable in the interior of interval convergence. And first, your derivative has power series representation, which can be obtained by doing term by term differentiation. And now starts from 1, Cn x minus a to the n minus 1. Because the first term becomes 0, right? Starts from 1. If you want, you can write it as C1, 2C2 x minus a, 3C3 x minus a squared, 4C4 x minus a to the third. Keep going. Secondly, your indefinite integral will be obtained. Your indefinite integral functions, an antiderivative of f also has power series representation, which is obtained by doing term by term integration, which means Cn over n plus 1 x minus a to the n plus 1. So some arbitrary constant plus C0 x minus a, C1 over 2. Keep going. Now, here, the antiderivative constant, usually we write it C0x, right? But I want to write it this way. Then, what is it? This is C0x plus minus C0a, C. So from here, C plus minus C0a plus C0x. Still, this is arbitrary constant minus some constant is arbitrary constant. So even if I write it this way, it's same as C plus C0x. Arbitrary constant plus C0x. That's why I just want to write it as this nicely. Alright? There's nothing wrong with it. And because anyway we have an arbitrary constant here. So, and most importantly, and the radius of convergence in 1 and 2 both are same as the original value. Original series, the powers, the radius convergence of the original function's power series representation will be preserved here. Okay? So, now, let me take a look at the coding. Okay. I think we're going to stop here. Okay? We're going to stop here. This is the short, but anyway, first part of section 8.6. Okay? Alright, so the next time we will cover the rest of section 8.6. Thank you. See you next time.